Today, I will give you the project lecture 2, and this is our last project lecture. And begin today, you can begin to do your project. And at the April 29, you will have an exam. It's an open book exam. Please pay attention to this. And now we begin talk about the project. Last week, we have talked about the DC motor modeling and the PID control, MATLAB and Simulink introduction. And 2 examples for DC motor PID control to Simulink. And the videos of 2 examples Professor Su have sent to you. If you never programming in Simulink, please practice it. Follow the video and practice it. It's the basic for your project. And today, we will talk 3 electronic actuation paradigms of exoskeleton, including the conventional actuator, series elastic actuator, and Quasi-Direct drive actuator. And after this, we will talk about the hip exoskeleton modeling and the hip exoskeleton bandwidth analysis, backdrivability analysis. After the 4 parts, you will know your project tasks. The project tasks is very similar with the 4 projects, so please listen carefully about the 2 parts. And at the end of the semester, you will require to deliver, everyone should required to deliver the final presentation video due the May 13, and the final report, 2 pages actually temple paper report due at May 20. And if your report is more than 2 pages, it's okay. And then now we begin the first part, 3 electronic actuation paradigms of exoskeleton. And now we have 3 actuator paradigms. The conventional actuator, series elastic actuator, Quasi-Direct drive actuator. The 3 actuator is now very popular in the world now, and began 20 years ago. From here, there are a lot of robots in the world. In the earlier, the researchers prefer develop the conventional actuator, include the hand exoskeleton, revoke exoskeleton, and an humanoid robot. And 20 years at the end of the last century, scientists developed the series elastic actuator, but in recent 10 years, it used in the robot and become very popular, like the UB-Teach and Cassie, the leg robot and animal, this robot, and some exoskeletons. And the last is Quasi-Direct drive actuator. The first time to talk about this kind of actuator paradigm is began from the 2017, the MIT Cheetah group. In this group, this is the MIT Cheetah and the MIT Mini Cheetah. You can find those 2 kind of robots that are heavy, and the Quasi-Direct drive is more lightweight. And if we talk about the robots, we will find the humanoid robot it just can work slowly and then work faster. It can jump, can work faster, and for the MIT cheetah, they can run faster and can. It's very interesting. Seems is for the mini cheetah, it can back flip. It's amazing. And the next, I will talk more information about the 3 kinds of actuator. For the first actuator is the conventional actuator. We can see the actuator paradigms. There is a small but long motor and a high gear ratio box, a stiffness transmission, and a leg. You can regard it as the load. And for the elastic actuator, it is the same motor, same higher gear ratio box. The difference is at here. They use a spring transmission to replace the stiffness transmission, and they use the same load. For the Quasi-Direct drive, we use a large director, use a large but shorter motor and a small gear ratio, and use a small load. Compare the from here. There are 3 important metrics to know which the actuator, the performance is better. The first is compliance, and it also you can regard it as the backdrivability. But what means the backdrivability? The backdrivability, you can see the video. High backdrivability means a low resistance. When we put on a force on the unpowered actuator, when rotate the rod, if it easy to remove it, that means it have a high backdrivability. If it hard to remove the output part, that means it's low backdrivability. Since the conventional actuator have a high gear ratio box, if at here there is a small friction, it will amplify to a large. And if here at a small, for the small motor initial, when we rotate the leg, we will find there is a relation between at here is the gear ratio can amplify the inertia as a cube. That means, for example, the inertia is 1. The gear ratio n equal to 100. When we rotate the leg, we will need do the work is 1 equal to 1000. So it will amplify, it will reduce a large resistance. And at here, why the scientists develop the elastic series elastic actuator? Because they use a spring to save the energy, and it can improve the backdrivability, but the SEA is use the trade-off the bandwidth to amplify the backdrivability. For exoskeleton, we hope we have a high backdrivability and high bandwidth, and because it has a small gear ratio, and for their motor, it can provide large torque, so we can get better performance. And what is the bandwidth? The bandwidth is a measure of how fast the system responds to the change in input comment. We can know it from here. We already know the Quasi-Direct drive have better bandwidth. So for the mini cheetah, it can run faster, can jump, can work, can do faster motions. But for the conventional actuator and serious actuator, they just work slowly. So that is a high bandwidth benefit. And the second, in a crew control loop, bandwidth defined as the frequency at which the closed loop amplified response reaches -3 dB, and the output gain equal to about 70.7% of its matrix maximum. If you understand what's mean of the two centers, it's okay. Just remember -3 dB and the 70.7%. Remember the two words. We will use it in the simulation part. For your project, all things is around the two metrics, bandwidth and backdrivability. And here we compare the conventional actuator. Since the series elastic actuator contains a spring element in series with mechanical energy, so it can trade off the bandwidth to improve the backdrivability. And here is a video to explain the series actuator, the SEA. And the next slide is the Quasi-Direct drive actuator. For this kind of actuator paradigms, it can eliminate the need of physical spring in the SEA and the stiffness modeling, Mechatronics, the sensor, and enforce torque sensors. And it can both have a high bandwidth and high backdrivability. And here is a video presented by Professor Su he talked about why the QDD amplified in the exoskeleton. I want to know, do you hear the voice?
No.
No.
You can't hear the video's voice?
No.
All we hear is your voice.
Okay. I try again. Can you hear the voice? Can you hear
No.
Professor Su's voice? No?
No.
No. What should I do? Can you hear the voice?
No.
Okay, I upload the PowerPoint to your Dropbox. After the lecture, you can listen the 2 videos. We only have 2 videos. You can listen the video, watching the videos by yourself, okay?
Professor, do you want us to watch the video?
Yeah, I hope you watching the video.
This
And
email.
I hope you watching the video because you were required to describe the 3 actuator paradigms in your describe the comparison about the 3 actuator diagrams in your final project report. And I want to you can watch it by yourself.
Did you send the
I'd hear
Professor, the video doesn't play if you download it.
And where can one download it? That's the question. Is it on our Dropbox?
Yes. And at here, I want to use.
Professor, I tried that and it's not playing. It says cannot play media if I try to play it after I download it.
You can download it in the PowerPoint. If you open it and click here, it's okay. Okay. At here for there is a experimental results about the bandwidth and backdrivability. This result is based on the real experiments. And for today, our our purpose is we want to get the Simulink results about the bandwidth and backdrivability. And from that video, okay, we begin our. And the next is the Quasi-Direct drive actuation, the backdrivability. We already know if the gear ratio is large, it will have low backdrivability. We can see the video. We need a large force to rotate the actuator. And for a small gear ratio, we can easily rotate the actuator. So now you already have a basic knowledge about the backdrivability. This slide is the Simulink result. Compare the 3 conventional actuator, SEA actuator, and QDD actuator. And we can find the result from this simulation result. In your project, you require to compare the 3 actuators. It's similar like this, and you require to draw the lines in the same figure. And here, the red line is the traditional robot. It has the lowest backdrivability. The backdrivability, the resistance torque is the backdrive. It can be explain the backdrivability. When the resistance torque is large, the backdrivability is not good. So at here we can find the traditional robot. It has the lowest backdrivability. It about 16.7 Newton meter. And for SEA, it has a small backdrive torque. And for the QDD, it has smallest the backdrive torque and the highest backdrivability. And this slide is about the bandwidth. For the bandwidth, the larger bandwidth is better. From the Simulink result, we can find the blue line is the SEA result, and the conventional actuator is 21 Hz, and for QDD is 65 Hz. And here we can find the SEA is more than the conventional. That's because it trade off the bandwidth to improve the backdrivability. So the result is reasonable. And how to read the bandwidth from the finger? The word is I added at here. So if we get the result, is only the figure, no word at here. So how to read it? For example, for the conventional actuator, the read line, we draw the -3 dB, draw a line at here. For this point, draw a line at here. This is this point is its bandwidth. We can read it from here. It's turn 20 and it's about 1, so 21 Hz. So the conclusion about the 3 actuator paradigms. The conventional actuator, it has higher bandwidth and lowers the backdrivability. For SEA, because it trade-off achievable bandwidth for higher backdrivability. And so it has lowers the bandwidth and higher backdrivability. For Quasi-Direct drive actuator, it has the highest bandwidth and highest backdrivability. After talking about the 3 electronic actuation paradigms of exoskeleton. Then we talk about the hip exoskeleton modeling. It's similar with the last lecture, DC motor modeling. I believe you remember the modeling steps. First, have a for the DC motor. First, we have a DC motor and get the electromechanical system and draw the and get the equations relations based on physical and electrical systems and get the transfer input output transfer function. For the hip exoskeleton, it is similar steps. Now we already have a hip exoskeleton. For this exoskeleton, there are two actuators. And at here, we only need to modeling one actuator. So we modeling the left one, the right one is the same thing. For example, so we draw the mechanical systems. In this hip exoskeleton, we also use the DC brushless motor. So the electronic part, the motor part is same with our last class, but it have a gearbox and have a transmission for in the human. For what should we notice that here there are two input and one output. This is different with our last lecture. One is the voltage of the motor, and another is the theta h. Theta h is the human joint angle, and the output is tau a. Tau a is the exoskeleton output. It is the exoskeleton. This is the how much torque can be assist the human. So when we analyze the modeling, we should consider two considerations. Next, we will consider the first section. If we fix the position of theta, that means the theta h, the human joint angle will be 0. And that here, the input is the voltage, output tau a, and we began this part. It's the same thing with our last week. From the electronic part, we will have the V equal to L, the L's voltage, plus the motor, the back EMF's voltage, and plus the R's voltage. So V minus VB equal to L times the time derivative of I plus Ri, and VB equal to KB, and the time derivative of theta. And the tau m, since the motor, it have a relationship between with the current. The tau equal to KT times I. KT is the motor constant. And for the electronic part, the tau m equal to Jm times the double derivative in time of theta, plus Bm equal to theta, the time derivative, plus the tau 1, the motor output torque. For the gear ratio part, there is a relation, the tau 2, the gear output torque equal to N times tau 1. N is the gear ratio, and theta, the angular of large gear equal to the a small gear's angle over the gear ratio. And for the transmission part, the tau2 equal to BCS times theta 2, the velocity of large gear minus the theta h, the velocity of angular. But at here, the theta h equal to 0. So the tau2 equal to BCS times the time derivative theta 2 plus Kc times theta 2. At here, we regard the tau A equal to tau 2. So the two equations are same thing. And for the variable structure, the tau H is the torque humor muscles plus the tau E equal to, oh, this is wrong. This is should be tau A equal to J. That means the muscle torque plus the exoskeleton torque equal to the JH times the joint, the accident of joint angle. Since the bandwidth simulation is fixed the human leg and test the bandwidth of the PID torque control, so if we fix the theta H from the modeling, we can get the bandwidth analysis. So based on the basic equations, we draw the control block diagrams and use a PID control and give a closed control diagram. We will get this. And the GS equal to tau A over VS. This transfer function is the bandwidth transfer function, and you will use it. You will need to derive it and description it in your final project report. And the second condition is unpowered. That means the voltage equal, the VS equal to 0. In this condition, the angle, the joint is the input, and the tau A, the exoskeleton output torque is the output. And this part is the same thing with the last, with this slides. The only different is the input and output. So we draw the control diagram will look like this. In this condition, we will get the backdrivability because we test the, when we input the angle of the exoskeleton, we will get the resistant torque of exoskeleton joint. So we can evaluate the bandwidth when the motor is unpowerful. And at here, the GS is the backdrivability transfer function. I hope you can think about the two kind of modeling by yourself, because you will required to describing this step by step in your report. The next part is the bandwidth analysis. For fixed position theta h, for this condition, we already have the control block control diagram. Look at this. And how to get the bandwidth is we need to, in the pointer is to set the input. And here we will give a trip function. What mean? The amplified 1 Newton meter and 0 equal to 300 Hertz and 30 minutes. This means for the input, we will give a sine function, and its amplitude is 1 Newton meter, and it will the sine fractions frequency will increase from 0 to 300 Hertz in 30 seconds. This is the Simulink code, and this part is to compare the output's amplitude. If the amplitude, at here we choose the absolute value, so the amplitude is more than 3 dB. It's also the 0.707. Do you remember? I hope you can remember two numbers, the 3 dB and the 0.707. It used at here. At here, if we see if the amplitude is more than 3 dB, it will return 0. And at here, I run for the code. We should set the gain at 1 Newton, not the 3. So when you programming, you pay attention to here. For our exoskeleton, for this hip exoskeleton, when we give the two variables, how it will influence the performance. And here we will only change the gear ratio and the stiffness. Okay, back here, if we give the two variables, the stiffness case and the gear ratio, how it will influence the bandwidth, we can get the answer from the simulation results. As we know, the bandwidth is large, and more large is better. So at here, the larger, the deep orange is better. So it requires a small gear ratio and a large stiffness, transmission stiffness. So we can think about for the conversion actuator, it has a large stiffness and a large gear ratio. So the bandwidth is okay, but not very good. And for the SEA, it has a small transmission and a large gear, so it has the lowest bandwidth. For the QDD, it has a small gear ratio, maybe at here, and a large transmission stiffness, so the QDD's bandwidth should at here. The next is an example. I want, since there will be a little difficult to get the simulation result of bandwidth, so I use the last lectures to analyze the bandwidth. This is our DC servo motor and the electronic motor mechanism and the transfer function. And we will use a PID control to get the position. And in this control, we will get this is the position control. In this simulation, we will analyze the position control bandwidth analysis. I already, you can download the Simulink code at here from the link, and there are 3 parts: the DC motor bandwidth, and the border amplifier, This is a function of the, we will use in the DC motor bandwidth. And here, this part is a simulation code. If the 3 files should in the same folder. When you run the DC motor bandwidth, you will get the result. Maybe wait 30 seconds. The result, you will only use this part. When you use the magnitude margin, the phase margin, you will not use. This figure is the systems border figure. And for the simulation code, if you click here, you will find a figure like this. That is because we set the amplitude. If it is more than 3 dB, it will return 0. So if you find it here, the result becomes 0. That means this point is the bandwidth. So we can find it here. It's almost 100. And at here, we also can find the bandwidth from this finger. We can get the minus 3 dB, draw a line, and draw a line. We will find it is also about the 100 Hertz. That is the 2 way to read the bandwidth. And we can think about this DC motor. We will find there is no gear ratio, and no gear ratio. That means the gear ratio equal to 0. And for this kind of actuator, this is the ideal actuator. But why we don't use the direct derivative motor actuator? This is because the motor only can generate a small torque. For example, for when human rock, the exoskeleton at least requires about 20 newtons. For this motor, it may be only generate 1 Newton or 0.5 Newton. It's too small, so that is why we need a gear ratio. That's why the existence of the conversion actuator. And after the lecture, you can practice the Simulink by yourself. And if you have questions, I will be here until 4:45. If you have a question, you can ask me. Please practice the example by yourself. Okay, and then is the backdrivability analysis. At here, we set the V equal to 0. You can find at here, there is no loop, control loop, no, there is no reference. That's because the motor is unpowered, so the PID control is useless. The microcontroller is unpowered, so we only need the systems transfer function, systems control diagram, and at here output our input begin. We will monitor the human's work. So we set the amplitude 5 degrees, and the frequency is 0 to 10 Hertz, and it is also used the trip functions, and the frequency will begin from 0 to 10 Hertz in 5 seconds. And from the control diagram, we will test the resistance torque of the exoskeleton joint to evaluate the backdrivability. So we draw the backdrivability control diagram. You can get the transfer function from this block. And at here, we will put in trip function at here. And this is the Simulink code. Since for the backdrivability analysis is much easier than the bandwidth, so I didn't provide the examples at here. And for the backdrivability analysis, we already set the two variables, the transmission stiffness Ks and gear ratio N, and we can compare the three kinds of control actuator diagrams. We already know the backdrivability. For the backdrivability, the resistance torque is small is better. So for the gear ratio, for example, at the if the gear ratio is 100, we will find that stiffness is large, the bandwidth will be better. And for the if the gear ratio is 0 and the stiffness is large, the resistance torque will be small. So for the SEA, the gear ratio should be at here, and the stiffness will be at here. So it has a small it have a better backdrivability than the conventional. And for the conventional actuator, it has a large gear ratio and have a higher stiffness. So its torque, resistance torque will be at here. It will be large. And for QDD, it has about less than 10. The gear ratio maybe is 8, and the stiffness will be seen as the conventional actuator will be at here. So we will find that it has a highest backdrivability. And the last part is your project. You have to submit 3 items: the final presenter video and the final report and the Simulink code. It is also due at May 20. And what should have in the report? First, you should compare 3 electronic actuation paradigms of exoskeleton. And the second is the modeling, the hip exoskeleton modeling. And give the details and the description for every steps and every equations. I have given the results on the PowerPoint. And when you think it by yourself, you can write the details. It's just some word to describe the equations. That's why I didn't tell very details about the modeling. And draw the control block diagram. You can also find from the PowerPoint. Drive the transfer function bandwidth. I have reminded you the answer, right? And drive the transfer function backdrivability. You can also find it from the PowerPoint. And for the simulation part, this part is the difficult part for you. You have to use the 3 the conventional actuator parameters and SEA parameters and Quasi-Direct drive actuator parameters to simulation to get the bandwidth result and the backdrivability results. And here is a hint. Since I already give the damage at here, there is a relation between K. For example, at here, the QDD QDD's diameter is 3 times the SEA's actuator. So it's KT, for this KT should times the 3. And for the J, it should times 9. And what you should deliver, the figure is, first is the bandwidth, compare the 3 actuator, and the backdrivability. The hint is you will only use the magnitude margin in the border figure. And the reference, there are 4 references related to the project. The first is the design and control a high torque and highly backdrivability hybrid software exoskeleton for knee injury pre-winter during. For this reference, it will have some results about the backdrivability and analysis. You can read it. And for this part is a bandwidth result and QDD. And for the third reference, it talks about a QDD. And for the last reference, this is the first paper talked about the SEA, QDD, and the conventional actuator. And at here, this actuator is it equal to QDD, just the different name. And if you have any questions, you can email me. And do you have any questions about your project tasks?
Professor, could you go back to the model of the block diagram in Simulink?
Okay. This one. Right.
Could you go to the Could you go down one to the one that it's showed in Simulink? Between motor electric component and motor mechanical component, what is that box with that like logistic curve looking thing?
Can you repeat your questions?
Right before the gain, but what is the block between motor electric component and motor mechanical component? Right after 1 over LF
Oh,
plus
here,
R.
this one. Do you mean this one?
Yes. What is that?
This is a limiter block. For example, at here for a motor, the voltage is limited. For example, at here, V theta is I can write it here. It used to limit the voltage. It will set the limited the voltage between 0 to 42 volt. And at here is the current limitation. How to set it? It is based on the real motor's parameters. I will write the limitation at here, and when you program it, you can use it.
Okay. Are the limits like how do we know what limits if we're just doing a simulation and we don't have the actual motor?
I will give you the parameters. I will give you the limitation to you.
You said you were posting the code or you were just showing us the code?
I post the bandwidth code for this example. For this modeling, I give the simulation code and M field, and for every steps, and I give the explanation. So when you learn the example, and you will know how to do this part. So for the next 1 hour, next 1 or 2 hours, you can practice the simulation code by yourself. And the link, I can send the link to you.
Professor, can you send the link to the drug box containing all the elements of what we studied in class?
Sorry, the signal is not very strong. Can you speak again?
Can you resend the link for all the work that we did in class this semester, you know, the drug box? Because it looks like my drug meeting
Okay.
is leaving out some
Okay.
other, some, you know, some other documentations. Just want
Okay.
to make sure that I have all the documents in the Dropbox. Can you send?
Okay, I will send you all the lectures and the links and the code links.
That would be very helpful so that we have all the materials together.
Okay. The project one. I can move the two project code to your Dropbox. Okay, it will be more useful.
That would be great.
Okay. Please wait a moment. I have put on the code on the student folder and in the project folder.
Thank you, Professor. Also, does it contain last week's lecture? Let me see.